This is you. You enjoy playing golf. And you also love the fact that your net catches all of your golf balls. But what if one time it didn't? Oh dear. I think we might have a slight problem. Hi, I'm Ratisha, and this is quantum tunneling, a quantum mechanics phenomenon in which a subatomic particle can pass straight through a potential barrier. Let's get going. In classical physics, let's take a ball on a hill. If the ball does not get enough kinetic energy to overcome the potential energy of the hill, then it will never get anywhere. But let's take an electron and a potential barrier instead. Sometimes this will happen, but other times this. Even if a subatomic particle doesn't have enough kinetic energy to jump the potential barrier, it can still appear on the other side. You're probably wondering how this all works, so let me explain it to you. First things first. Unlike a ball, you can't pinpoint the exact location of where an electron is going to be. That's stated by the Heisenberg uncertainty principle. Instead, you know the probabilities of where it's going to be. With this is called a wave function, and it shows the high probability and the low probability of where an electron is going to be. So now, instead of imagining a particle going towards a barrier, let's imagine a wave going towards a barrier. The wave gets reflected by the potential barrier. What about the whole tunneling thing? To imagine what a wave function would do when it came into contact with the potential barrier, let's look at another kind of wave, an electromagnetic wave, or more specifically, light. When you shine a light beam through a prism, eventually you find total internal reflection, where 100% of the incident ray comes back as 100% of the reflected ray. But that's wrong. In fact, if you look closer and solve Maxwell's equations, what you find is what's called an evanescent wave, which is modeled by the equation y equals e to the negative x power, or exponential decay. So now we add that back in, and this happens. When we solve for Schrödinger's equation, which tells us the amount of energy needed in a certain quantum mechanics system, it tells us exactly what the evanescent wave predicted. It is exponential decay, and there is a small but non-zero probability that the particle may pass the potential barrier. Even though the probability of quantum tunneling is so small, there are so many quantum particles in any physical reaction that they add up, making quantum tunneling fundamental to things like nuclear fusion in stars, spontaneous mutations in DNA, or even substrate enzyme reactions. You might be wondering, since subatomic particles can pass through potential barriers, can't humans as well? And the answer is at this point, no. Planck's constant, a part of the Schrödinger equation, states the larger the mass of the object, the less likely it is to pass through solid walls. But the field of technology and the field of science is still ever-changing and ever-developing. So the real answer is, maybe.